This is our first example problem, chapter 6, and what we have here is design a circuit whose 3-bit output is 2 greater than the 3-bit input. Outputs that exceed the 3-bit range should be set to 0. So first step in every circuit is to draw the interface, which is the black box diagram. This problem is kind of special because it doesn't really specify how wide the output is, and so you have to look at this thing. So it has a 3-bit input, so we can draw that, and we'll name it something like A, B, and C just to keep this problem short. And outputs are, the inputs are a 3-bit number, right? So the outputs are going to be a 3-bit number also. Outputs are going to be 2 greater than the input, though if I hit 7 on the input, the output's going to be set to 0. So anytime the output exceeds a 3-bit range, which is 7, the outputs are going to be set to 0. Essentially what I need in this thing is to be able to go up to 7 on the output, which requires 3 bits. So I will put those at 3 bits on the output, and I'll call them, should I call them F2, F1, F0 for lack of better words here. And I'm going to indicate those with arrows saying that they're outputs. So that is black box diagram. That's the first step in any digital design solution. So let's go from there. So this is iterative design, brute force design. We only know one design method, so let's do it. And what I'm going to do here is set up a table and go through every possible combination of those 3 inputs. So this circuit has 3 outputs, so I gotta put all 3 outputs there. F2, F1, F0. And what I'm gonna say in this thing, put some extra information there. A equals most significant bit. C equals LSB. Also F2 equals MSB of the solution, and F0 equals the LSB of the solution. So we're ready to go here. So the output is 2 greater than the input. So for this first row here, notice we have in the table itself, we have 3 inputs, so we're going to have 2 to the 3rd possibilities. So this table does in fact have 8 rows. So here we go. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. And if you look at this, it's just essentially a binary count after this point. 4 plus 2 is 6. 5 plus 2 is 7. Now 6 plus 2 is 8. What we said here, if it exceeds 7, I'm going to set the outputs to 0. 7 plus 2 is 9, which exceeds 7, so I'm going to set that to 0 also. This is our truth table. This represents the second model of this solution, with the black box diagram being the first model. So this is your black box diagram. It happens to be a high-level black box diagram. So next here, we want to write some Boolean equations describing this circuit. So there's 3 outputs. I need 3 Boolean equations. It's the same thing I've done before. This is kind of a grunt worky. What I want to do for this F2 column is figure out where the 1s live and write an expression for the inputs associated with those 1s. So we'll do that. If you look at the F2 column, it has 4 1s, so I'm going to take a shortcut here. Put my pluses in there, and then I'm going to look at these where this 1 lives. So right here is a 1. You can see that A and C are complemented. Okay, so here's your next one right here. You can see that A is complemented. A has a 0, which is we represent with a complement in the equation. Here is the next one. We see B and C are complemented. Here is the next one. We see that B is complemented. And there's my equation for F2. Okay, so I'm going to continue on here. I think I'm going to probably chop this out of the video. A, B, C. I notice I have 4 1s here, so I'm going to write 4 terms here and then go back and fix them up when I'm done. Okay, so back again, F0, I chopped this out so you didn't have to sit through this thing. I chopped out the writing of these equations. There's 3 ones in the F0 column, so that means I only have 3 terms. So let's fill in this F1 here. This first one, I can see that all 3 of these input variables are going to be complemented. For the second one, I can see that A and B are complemented, so these 2 zeros here is what makes me complement these 2 terms right there. Okay, what else do we have here? We have B and C complemented, and lastly we have B complemented. The F0 column, we have, once again, we have B and C complemented, we have A complemented, and we have B complemented. Those are equations describing our circuit. Next thing we want to do is draw this, and I'm going to draw this. This is going to take too long, and so I'm going to point out something to save time on this. This is going to be essentially a giant circuit. I'll kind of draw what it's going to look like. This is F2, F1, F0. Then these are the OR gates that are ORing all these terms together. Unfortunately, we have a ton of AND gates sitting back there. But one of the things that worth noting in this is that I can reuse these terms. So, for instance, looking at this, well, let's look at this term. If you look at this row, that there's a 1 in each of these outputs, which means we only need 1 AND gate, and we're going to feed that to all 3 of these OR gates. This is going to be A, B gets inverted, and C. Okay, so that's not too bad. I mean, we saved a lot of time on that. Instead of drawing 3 different AND gates, we reused the 1 AND gate 2 extra times. And so I can see that I can reuse this gate, I can reuse this gate, I can reuse this gate, and so in the end I'm gonna have a bunch of AND gates here. I'm gonna call this problem done just to save the grunt work, and it's going to be a big problem. It doesn't really, you don't really learn much by drawing this thing, but the important thing here is that if you look at these things really carefully, you can actually reuse some of these terms.